Biology students, this is the next video on chapter number 5 on weathering, the breaking down of rock into sediment. And sediment can be broken down into particles of different sizes, going from gravel to sand to even smaller to silt to clay. We talked about frost wedging before. We talked about thermal expansion. Next type of weathering we're going to talk about is called exfoliation, also called unloading or pressure expansion. But we're going to use the terms exfoliation and unloading. The best way to imagine that is when you have, let's say, imagine for a moment that you're standing on these rocks here, and you have a knowledge of igneous rocks now, and you can see it's pink in color, and it's phaneritic. It has crystals big enough to see, so you already know that this is a granite, and this is a plutonic rock. The first thing that should come into your mind is, well, this granite cooled deep underground, allowing for the crystals to grow large. But now it's exposed at the surface of the earth. So, logic would tell me, and should tell you, that whatever rocks were over this granite, because this granite cooled underground, have been eroded away, exposing this granite now at the surface of the earth. This granite used to be maybe hundreds or thousands of feet underground, overlain by other rocks, and those rocks were eroded away, and now the granite is at the surface of the earth. So way back in time, that granite was underground, under a lot of pressure from the overlying rock. But now this granite is at the surface of the earth, and it's not used to these low pressures. And the way it responds is by peeling off. That's what we call exfoliation or unloading. Here you can see the granite is breaking off in these sheets. Exfoliation. Think about going into this, getting sunburned. If I'm in the sun too long, my skin's going to peel off, right? You're sunburned. Well, that's exfoliation for human beings. But exfoliation for rocks, instead of the skin peeling off, the rocks peel off. And they make these structures called exfoliation domes. And there's probably the most famous one is Yosemite Dome in California. Here you have a granite, and it's peeling off and makes this round dome of igneous rock. Or another example closer to home would be Stone Mountain, Georgia. Here you can see Stone Mountain, Georgia. Notice how the granite is peeling off. It's shedding rock, and it's making it smooth, making this dome-like structure. Here you can see the exfoliation quite well. It's peeling off. This is the third type of mechanical weathering, when you have plutonic rocks that form deep underground, and the rocks above the pluton have been eroded away, and the granite explode, or the granite or diorite, they respond by peeling or exfoliating. That's the third type of mechanical weathering. Fourth type of mechanical weathering is biological activity. Whenever you get a driveway or sidewalk put in on your house, do you notice that the contractor will always tell you to cut down the trees? Why is that? Well, because the tree roots are going to force their way into the little crevices and cracks in the driveway and tear the driveway apart. That's biological activity. If tree roots can tear your concrete driveway apart, don't you think they could do the same to rocks out in nature? Sure. So animal activity can also tear apart rocks as animals dig holes in the ground. Ants do it, insects do it as well. They burrow into their tunnels and they tear apart a rock piece by piece, expanding their network of tunnels. So biological activity is another way that you could tear apart rocks mechanically. Fifth way is salt. Here's a place in Salt Point, California, appropriately named. And you can see that the salt crystals have grown into this rock and formed these open cavities in the rock. So if salt crystals grow in a rock, they'll make these, they will tear the rock apart, push it apart, and then when the salt dissolves, they'll leave this honeycombed structure, which can easily be torn to pieces by other forms of weathering. So you got 5 kinds of mechanical weathering you need to know about. Frost wedging, important up in colder climates. Thermal expansion is real important where there's a big difference in temperature between night and day. Unloading, when you have plutonic rocks exposed to the surface of the earth. Biological activity, that means plants and animals and insects tearing apart rocks. And the growth of salt crystals in rocks can break rocks apart. This is real important, ladies and gentlemen. This diagram here, what's the author trying to convey to you? Well, here you got a big blue cube, and then you've broken that one big blue cube into 4 cubes, and these 4 cubes occupy the same volume as this cube, and you break each of these cubes into 4, and then it gives you 16 cubes. What's he trying to show you here? He's trying to show you that's what mechanical weathering is. You're breaking rocks into smaller and smaller and smaller pieces, but you don't lose any rock with mechanical weathering. That's the important thing to remember. You don't lose rock with mechanical weathering. You just break the rock into smaller pieces. Chemical weathering involves the actual physical destruction of the rock through water getting into the rocks. And there's 2 main kinds of chemical weathering you need to know about. Acid dissolution and oxidation. Let's take a look at that. Acid dissolution and oxidation. So let's do acid dissolution first. Do you remember what happened when you put acid on limestone or coquina or marble? They all had the mineral calcite in it. What happened was that the acid ate its way into the rock. It dissolved the rock, right? Well, the same thing happens to rocks in nature. Rocks can dissolve when acid is applied. And what is an acid? Okay, let's do some basic chemistry here for acid dissolution. We got different kinds of acid. We got carbonic acid, which is H2CO3. We have hydrochloric acid, which is the kind you used in your rock and mineral sample kits. You have sulfuric acid, which is H2SO4. And you have, hydrofluoric acid. One more, hydrofluoric acid, which is HF. Each of these involves the formation of hydrogen ion H plus let me see, let me see. There must be a picture of this acid dissolution reactions. Okay, for example, here's one of them. H2CO3 is called carbonic acid. It releases hydrogen ion and bicarbonate, HCO3 minus. So an acid is any chemical that releases hydrogen ion, H plus. And this can dissolve rocks. Acid dissolution, any acid can dissolve a rock. Some minerals, though, are more likely to dissolve, especially those that have calcite. Second type of chemical weathering is called oxidation. Okay, let's take a look and see how oxidation works. You'd think they'd have a chemical formula here somewhere. Okay, I'll just write one in for you then. Okay. Remember, think back to when you were a little kid. Iron, Fe, plus oxygen in water. Good Lord. Oxygen in water gives you, I need an arrow key, but it gives you Fe2O3, which is, so when you have iron, imagine that you have some tools and you left them in the yard. What would happen to them if it rained? Rain carries oxygen, and it would cause the iron to turn into Fe2O3, which is hematite. Most people call it rust. All metals are going to oxidize. Iron becomes iron oxide. Copper becomes copper oxide. So if you look at some of your old pennies in your coin jar, some of them have a greenish tinge to it. That's copper oxide. You look at your grandmother's old silverware. It's tarnished. That's silver oxide. Do you think that the oxidation of metals will weaken or strengthen the metals? Which is stronger, a new tool that you bought at Home Depot or one that's rusted out in the backyard? Obviously, one that's rusted in the backyard is going to be weaker. And the same with rocks. Rocks that contain metal minerals in them, they can become oxidized, and that will weaken the rocks. And it can also cause the rocks to dissolve. So another type of weathering is oxidation, and that's especially important if you have metals in the rock. Now, next thing you want to think about is, don't forget, mechanical weathering breaks rocks down into smaller pieces of sediment, whereas chemical weathering actually dissolves rocks. But think about this for a moment. If rocks are dissolved, do you think they're going to get rounder? Do you think they're going to lose their edges and their corners? Yes. So when you dissolve rocks, you're going to lose the edginess or the angular look of rocks. And there's an effect of climate here as well. What is climate? Climate is the weather conditions over an area for the long term. That means precipitation and temperature. For example, we could divide climates simply into hot, humid climates, like Tennessee during the summer, most of the year. The southeastern United States is generally hot and wet. Hot, humid climates. We could have hot, dry climates, such as Arizona, where you get very little rainfall, but it does get up in temperature. You have cold, wet climates, like England. It's very cold and wet. Then you have cold, dry climates in places like Siberia and northern central Canada, where it's cold and dry. So if we compare these four types of climates, cold, dry, cold, wet, hot, humid, and hot, dry. We can also use the word arid for dry. So we got those four climates. In which of those four types of climates do you think chemical weathering will be more important than mechanical weathering? Well, think about it. Chemical weathering needs water. Therefore, the wetter climates will favor chemical weathering. Also, from basic chemistry, you know that the higher the temperature is, the faster chemical reactions proceed. Therefore, in parts of the world where you have hot, wet climates, hot, humid climates, such as the southeastern part of the United States, Southeast Asia, Brazil, you are going to have lots and lots of chemical weathering. Let's take a look, for example, at something that we have here in Tennessee and in all hot, humid climates. We have what we call karst topography. What does karst topography mean? Well, it means you have lots of caves. How do caves form? Well, caves are almost all made of limestone. Some of them are made of dolomite, but limestone, that's what most of the caves are made of. So when it rains, the rain is slightly acidic. It's filled with carbonic acid. It's going to dissolve the limestone, and these areas underground are going to be filled with water, and they'll dissolve out these caverns. Once the water drains out, you're left behind with a cave. Karst topography, K-A-R-S-T, is associated with caves. It's associated with, look at how dissolved looking these rocks are. They're very rounded. They look dissolved. You can see that chemical reactions have been dissolving the rocks. And we get sinkholes too with karst topography, K-A-R-S-T. That means we have these caverns that fill. Sometimes houses fall into them. I'm sure you've seen this happen. In Oak Ridge, a whole street fell in. It was called Mona Lane because the underground caves have a thin ceiling, and then when you build on top of that, the rocks on top of the cave will collapse, and the houses will fall in, and you'll have a big sinkhole. K-A-R-S-T. The chemical weathering is going to dominate in hot, wet climates and produce karst topography with caves and dissolved-looking rocks and very rounded landscapes and sinkholes. Where do you think mechanical weathering is going to dominate then? Well, mechanical weathering is going to dominate when it's colder. It could be cold wet or cold dry. Because in colder places, chemical reactions are slower. And so one can look at the Appalachian Mountains that we have here in Tennessee. Notice how rounded and dissolved looking they look. They're very rounded. They look dissolved. Chemical weathering is dominating here in eastern Tennessee. Now let's go out to the Rocky Mountains, where it's colder. And the mountains stand tall and they're jagged and angular. Why? Because frost wedging is tearing apart the rocks instead of chemical weathering. There is a relationship, too, between mechanical and chemical weathering. If you break rocks down into smaller and smaller and smaller pieces, it's easier to dissolve them, isn't it? In other words, the more mechanical weathering you have, the faster chemical weathering can proceed. Think about it like this. If you take a cube of sugar and put it in your coffee, and your friend puts granulated sugar in her coffee, the same amount of sugar, whose sugar is going to dissolve faster? The granulated sugar. Why? Because more surface area of sugar is exposed to the coffee. Same with rocks. The more you mechanically weather the rocks, the faster they will chemically weather as well. Look here. This is in France. Actually, it's pronounced France. But here in France, look at these rocks. Is chemical weathering dominating here in France, Mine France, or is it mechanical weathering dominating? As soon as you look at that, look at all the dissolved little caves in here and the rounded landscapes. This is southern France, so this is probably limestone. Chemical weathering is dominating here. This is karst topography. If you've ever been to the Lost Sea or any major cave, you see stalactites and stalagmites. That's from the dissolving of the rocks as the water drips through the ceiling and dissolves rock, and it comes down in these stalactites, or on the bottom, stalagmites. Oxidation, metals will oxidize. It's the second type of weathering. Now, erosion involves the weathering and the removal of that weathered sediment by water, wind, or ice. That's what erosion means. Next thing we're going to talk about is soil. And you might think, wow, what a boring topic, soil. Well, ladies and gentlemen, it's a very interesting topic. I'll tell you. The science of soil is called agronomy. And a person who studies soil, he or she is called a agronomist. You can get a degree in agronomy at the University of Tennessee, and it's very important. Think about it like this. Maybe 3 to 4% of the people in the United States are farmers, but we have enough food to eat in this country. Why? We have enough food to eat because we practice modern soil science, otherwise known as agronomy. We manage our soil resources so that every acre of ground produces the maximum amount of crops. Soils are absolutely important to the survival of the human race. If you look at other countries where they don't practice modern agronomy, people end up starving to death. Soil is made up of two things. Soil is made up of humus, Humus, and regolith. So soil is a mixture of humus and regolith. What is humus? Humus is decayed animal and plant material. It's what gives soil that black or dark brown rich color. It's what gives the soil its productivity. If you go in your backyard right now and you look at all of the layers of leaves from past years, they're starting to decay, producing what gardeners lovingly call compost. That's humus. Humus is leaves that have decayed over many seasons, earthworms that have died, insect parts. It's plant and animal material that's decaying. Regolith, on the other hand, is weathered sediment from weathering. So it's gravel, sand, silt, or clay. Soil is a combination of humus and regolith. We're going to continue on with this. I got to do something now, but I'll make another video soon.